This video is an introduction to the scalar theory of everything, the STO. The STO is a Kuhnian type of paradigm shift. That is to say, it's accurate, it is empirically agreeable with observation, it is consistent, it's internally consistent and externally consistent with other successful theories. That is to say, it corresponds to general relativity and quantum mechanics. It has a broad scope. It explains general relativity, quantum mechanics does, and it explains some of their problem observations. The STO is simpler, Occam's razor, and it is fertile. It suggests new phenomena or new relationships between phenomena, and it has made some predictions which are later found. Rival paradigms are incommensurable. So the Big Bang kind of models are not be too helpful here in thinking about or understanding. The STO fundamental postulates are that it accepts a fractal universe, that is, they self-similar, so we can take observations in our size scale and at least the equations of those observations and apply them to the kind of things that are in the smaller and larger size scales. It accepts the spherical principle. That is to say, forces are going to be inverse square proportional to the radius, which is the surface area of a spherical area beyond the source, and the potentials are proportional to the inverse radius. The two constituents of the universe from ancient times, people have seen that there were discrete things like trees and rocks, and then there are continuous things such as water. In the STO, the discrete things are called hods, and the continuous stuff is called a plenum, which is kind of like an ether. And I use the term plenum, which follows Descartes, to distinguish it from other types of ethers. And the problem the STO then has is to determine what the characteristics of these two things are. Now, the STO starts with experiments and observations data. That is to say, it looks at the data rather than what other people think of the data. For example, when you look at the redshift of galaxies, normally a lot of people refer to that as a Doppelshift, but a Doppelshift is a model of the redshift, you see, and that assumes a model. So we don't do that. We look at the data. In the Michelson-Morley experiment, people assume that it doesn't show the luminiferous effort. Well, that's true, it doesn't. But then we have a plenum. And what the data does show is that there is an effect that they found. It's smaller than what they wanted, and it's in the wrong direction from their viewpoint. So we start with the raw data. The universe is basically cause and effect physics. But where the cause effect is unclear, the math can use correlations among data points to help develop the cause effect. We see these correlations and the probabilities and that kind of thing being used in quantum mechanics, but all that means is we don't understand what the cause and effect is at those scales. Bodies, that is to say hot assemblies, have three dimensions and have a position and velocity relative to other bodies. Time in the STO is only now. No past, no future, there is only now. And it's called the streaming now. We note that physics postulates are generally time symmetric, but what I want to do is develop cause-effect, so it's cause and effect in the next now. I start with Newton, and Newton has two books, the Principia, which everybody seems to know, and Optics, which in the 1690s and so, Newton didn't know what gravity was, and he said so. In Optics, which started in around the 1700, and I used the 1730 edition, he started to rethink that, and he actually did, in my opinion, come up with a bunch of speculations about what was going on, that is to say, about gravity. In the Principia, Newton identifies three types of mass characteristics or body characteristics. weight, inertial mass, and gravitational mass. You'll note this is different than what the modern theories, they talk about one type of mass. So the Lagrangian and the Hamiltonians talk about one type of mass, and then they try to lump all this in there, which to me is a source of several problems that the modern theories have. What the STO does is it measures position and velocity of fallen bodies. Remember, that's what we said. Then what Newton does is he mathematically transforms it to a mathematical symbol, which is he calls force. In this case, the inertial force, which is not measured. It's transformed quantity calculation through something he calls a proportionality constant, which is inertial mass. Then he transforms gravitational mass to another type of force, the gravitational force, which then he treats like a continuous substance and its effect on a falling body, which is the gradient of the quantum. Then you set the F's equal and do the calculations, and everything else is well known. In his book, Optics, and again, this is where he's going to be developing a speculations about what gravity is. So he expanded on how the gravitational mass may be impressed on another body through the weight in relation to gravity and light, stated in modern terms. The bodies is query one in optics. Bodies bend passing light around an amount inverse to its distance. Light passing close to edges are diffracted in fringes. You know, this is the beginning of the small world, that is to say, interference. Light path begins to bend before reaching a body or a slit. Now, this is a little different than what most people today tend to think. But Young, in his experiments later on, also thought he saw light beginning to bend before it actually reaches a body or a slit. And that is not accounted for in current theories, because in interference experiments, the light has to pass through the slit before it bends. Black bodies absorb all light. Black body radiation is kind of understood. Sun and stars are black body radiators, of course. Light is corpuscles, particles, Newton speculates, and they are pushed around, which is the divergence of the ether's density, by waves in the ether that overtake the rays of light. Overtake means the waves are traveling faster than light. It's not a big stretch to say much faster than light, which the STO does. That is, say, gravity is not force. Gravity is the effect of the divergence of the ether. Also, like a rock thrown into water. You note this is two things. It's the rock and the water. It's the corpuscle and the wave that's what give you interference. A medium that refracts and reflects light also allows light to heat bodies. Sure. Refraction of light implies differing densities in the medium. Increasing ether density causes light refraction. Yeah, that's just 21. Rarer ether is within dense bodies, such as Earth, and increases with distance, thereby causing gravity of those great bodies. Everybody is endeavoring to go from the denser parts of the ether to the rarer. That's the attraction of gravity. Newton was suggesting a reductionism step by positing an ether whose divergence exerted a force, weight, that caused gravity, that caused the diffraction, reflection, and refraction of light. Corpuscles as light and as components of matter. That is to say, support for the ether and corpuscles was because the model could explain several diverse observations, then known but mysterious, rather than by direct observation. Newton was speculating about a theory of everything, period. The next step in the STO was the quasi-steady state cosmology. This model, which came about in the 1990s through the early 2000s, added that the stuff of our universe continually enters through sources at the center of galaxies. It added a creation term to the right side of the general field equations. Now, you'll note this is a lot different than Big Bang, which had everything created all at once. This model accounted for rotation curves, which the Big Bang model needs dark matter, and other unexplained general relativity observations. That's its advantage. This is a book. Scalar is still pursuing this, so you can look them up on arXiv and see some of the papers. Note we're dealing here with forces, not energy. This is Newton's model of forces. The action-reaction is that bodies cause plenum changes, that is to say the gravitational mass of bodies cause plenum changes, and the plenum directs the Hodds. This is the universal equation. This part is the rho density, which is the plenum density, at some point in space. This part is from source galaxies, otherwise known as spiral galaxies. This part is from the sync galaxies, which are elliptical galaxies, and this part is from all Hodds in the universe. This quantity and this quantity are source and sync strength of the galaxy sources and sinks. I use the B-band luminosity, but more about that later on. This is essentially the gravitational mass of each Hod, which is yet to be calculated. After calculating the rho density at a point, we then take the gradient of the rho and apply it to the normal of the surface of a Hod to determine the force on that Hod. And then that force is going to direct the Hod, and of course, later on, all bodies in motion. You will note that this equation is Machian, which general relativity is not. And as far as I know, this is the only really Machian thing that's going to use. It is causative in that the sources, the sinks, and all the matter in the universe cause the plenum density at some point, which then exerts forces. The application of the spherical principle here has 3 and only 3 spatial dimensions. This force is the only force and is going to be magnetic, and we're going to get into that here in a little bit. Therefore, the speed of the force determines the time characteristics. The speed of change in the plenum waves, is much greater than the speed of light. Van Flandern measured this relative to the sun. Stefanovic looked at it from the speed of Coulomb forces. And these are 2 video on YouTube that are very interesting, determining speed of the entanglement in quantum mechanics. The speed of Hodds is the maximum speed, is the speed of light. And that is according to the Lorentz-Ether theory. Now, this is the maximum speed of anybody, is only the speed of the Hodds or the photons. It is dependent on rho, and because it's dependent on the plenum density, it can change. That is to say, we're looking at a variable speed of light theory here. All interactions. Our Hod causes waves in the plenum waves propagate faster than the speed of light, and then the plenum gradient on the Hod surface directs the bodies. This is Newton's weight, as we see. Therefore, all interactions are, to put it in the phrase of Bell's inequality, all interactions are non-local. We're going to start by looking at the small. The key to understanding the small for a particle model, a photon model, is diffraction and interference. One of the huge problems that we have to overcome in looking at interference is coherence. Coherence is a huge problem for particle models. What exactly is coherence for particles? Young's experiment was accepted and interpreted because it suggested wave-like behavior because it seemed the only explanation of coherence, which was shown in diffraction and interference experiments. We know that the Afsar experiment rejects Copenhagen interpretation, which is wave-particle duality, and some other interpretations in quantum mechanics. The Stowe explains how coherence occurs for particles, and that is a big thing that particle models had to overcome. Soon we'll be talking about a transparent mass experiment, which rejects all models of light, except for the Stowe. What is a HOD? In the Stowe, we have found that the Stowe is a magnet whose plenum evolves to gravity, and we're going to see that. This model came about in conversations with Andre and Emmanuel here. At the time of those conversations, they were looking for monopolar magnets. Emmanuel likes spherical magnets. I like flat magnets or disk magnets because they can form structures. Andre developed an experiment where he was looking at repulsive effects of magnets. And as far as I know, nobody else had done this before, but Andre had a issue, and his issue was that he measured only a very narrow range. So I built a different apparatus here to measure repulsive strength of magnets. You see that here's an upper magnet and a lower magnet, and this lower magnet is attached to a weight scale. And what we're going to measure here is the repulsive force that the upper magnet causes on the lower magnet. There are 5 papers that I looked into this. Andre's data was in what I call zone 3, which is in this zone here. Now, the force varies in this range approximately as 1 over the distance cubed, which Andre determined. The problem was that this is also well fit by an exponential equation, and the data cannot decide between the two. I looked at data that was much further. In the zone 1s there, the force varies as 1 over the distance. In zone 2, the force varied as 1 over distance squared. Paper 5, and where we're looking at is right in there. That is the asymmetry, which, as we'll see later on, we're going to propose evolves into gravity. The following video is a quick little demonstration of what we're talking about here. Here we have a glass tube with a wood dowel inside. And these are magnets, very strong magnets. I've colored the North Pole black and the South Pole red so that you can see it. I'm going to insert this into the tube. So I insert these into the tube. The tube is slightly larger than the magnets so that they'll stay nearly axial. And let me see, we're looking at the North Pole first. So as you can see, the North Poles repel each other. Now let's mark North Pole repelling distance by the white paper strips. Now we're going to reverse the poles. Now you can see that the South Poles are closer together with the same weight on the top, and they're slightly closer together by approximately the width of one of the magnets. Therefore, the repulsive strength of the North Pole is slightly asymmetric to the South Pole. No, electromagnets do not show asymmetry. This then is a HOD. High level rho to low level rho, these are the force lines. One side is stronger than the other, and so one side has force lines which do not terminate on the other side, and this is what evolves to gravity for distances greater than the atomic scale. You'll note then that Newton's force law for gravity is simply an approximation of what's really going on at the small scale. The Stowe has noted an inconsistency between Faraday's law of induction and Ampere's circuit law. That is, there are two different types of magnetic field, and that is explored in the paper that you see there. Faraday's law of induction is that a permanent magnetic field moving produces an electric field in a conductor. A changing current in an electric field produces an electric magnetic field. This is the Biot-Savart law. You'll note that a cross product of the current introduces a magnetic field at some point. That is to say, the current along the entire length of the wire produces that current. That is what we're going to explore with an experiment. Here I have two disc magnets. If you'll note that if both sides north is up, they repel. If one is north and the other is south, they attract. We're going to use this to detect current in the wire and the resulting magnetic field. Here is this magnet. I've attached it to a piece of wood and mounted it on a weight scale. Now there's a small gap of about 0.5 millimeter here, and we've attached two wires that's going to provide current. Here then is a multimeter. I turn it to the resistance range, and you see it's measuring about 0.4 of an ohm through this current path. Let's change back to voltage. Here is the battery. And what I'm going to do is attach the terminals to the battery. Now, this is not, there's some problems here. When I attach the terminals, the battery is going to provide a lot of current. It's going to actually discharge the battery faster than it should, and therefore things are going to get hot, and the battery's not going to last too long. And the current level is going to be varying. So we need to be quick about this and not take too much time in the actual measurement. I'll attach one terminal. I'm going to turn on the scale, the weight scale. It's reading 0 because it's zeroed with that weight on there. So, let me attach the battery. You see that we're measuring a voltage, which means the current is flowing. And this is reading 0.36. The next experiment is to move the electrodes here very close to the magnet. Now we're measuring 0.39, which is very close to what we had in the full length of the magnet. That means the current and the magnetic field produced in this part and this part are having no effect on the magnet here. It's only the current over the magnet. To see this, let's do one more little test. Here, all the current is going to be on one side through the brass bar here and not over the magnet.
We're getting a voltage reading, we're getting current, and the reading here is 0. That is to say, there's current flowing here, but there's no magnetic force being exerted on that magnet. This means the Biot-Savart law is rejected.
The experiment indicates the magnetic effect is ejected from the wire perpendicular to the wire, but not at any other angle. This is also experienced in radio signal antennas. The Stowe suggests the Hods have a magnetic field and travel at the speed of light compared to the plenum wave, which travels at many times the speed of light. This is a diagram depicting another experiment we're going to do. We have a coil of wire that surrounds in a magnet, which is in the middle. In the Stowe model, only current from perpendicular to the wire will have an effect as depicted in the C2 areas with delta equal to 1. In the other areas, perpendicular to the wire does not overlap the magnet. Magnets on a scale, and I'm going to measure the force that is exerted on the magnets by the coil of wire. This is the coil of wire with a power supply that's going to provide about 1 amp of current. We place the magnet in the coil and measure the force that when the current flows. In the center, here as you see, and later on at various radii here near the edge of the coil. This is a plot of the result where the force at some radius is compared to the center force, and the bottom line is both the data and the Stowe line plotted, and the upper line is what the Biot-Savart law says it should be. You can see that the actual result agrees with the Stowe and not with the Biot-Savart law. Faraday's law concerns moving magnets, so we're going to drop a magnet through the coil with a voltmeter attached. The voltage measured from the center drop to an edge drop is the same. This suggests that a magnetic field induction is dissimilar to the electric field characteristics in the Biot-Savart law. Maxwell's equations should be redone and should include causality. Photon diffraction is a central mystery of subatomic particles. Some observations of light suggest a particle model of light, such as the photoelectric effect. Other models suggest wave model, such as interference and diffraction. To have a better model of light, we need one of two types of models. One, either create a wave model of the particle experiments or create a particle model of the wave experiments. And that's what we're going to do. We're going to create a particle model of interference. The challenge of uniting the Newtonian and quantum worlds is to develop laws of motion of photons that obtain the diffraction experimental observations. Young's experiment, of course, was taken to indicate light was a wave primarily because it was a way to model coherence, and that seemed to be what was required for diffraction. The light that passes through a slit is allowed to impinge on a second mask in Young's experiment, and that produces the interference pattern. Coherent light is, by definition, light that produces a diffraction pattern on a screen after passing through a slit or a pinhole. Coherence, as far as we know, is obtained by either a pinhole in the first mask, such as in Young's experiment, or by light traveling a long distance, such as from a star, as seen in the area telescope pattern images, or from a laser. The model of a photon started with Democritus. He talked about corpuscles, that was the Newtonian term. But light has many different colors or energy levels. Therefore, photons cannot be a single type of particle. That is, the Stowe photon is an emergent entity of Hods, which are the corpuscles, and plenum, which is an ether. The number of HODs in a photon determines its energy. The photon model in the STO is a column of HODs, and since photon monopoles have not been observed, therefore there are only magnetic dipoles. So we take a HOD, a magnetic dipole, and a 2D particle, which composes all of the bodies, and therefore HOD is a magnet. And we form them into a column, which you see here. And the plenum impinges on the surface in this direction, but then from the other direction, this way, there is no surface area, which means the HOD is going to travel in that direction and travel with the fastest speed possible because there's no surface area here. As it travels, it's going to emit waves, like here, forward and backward. Emitting waves forward is then going to sense what is ahead of the photon and reflect those back. Remember, these waves are traveling much, much faster than the speed of light, than the speed of the HODs. And therefore, we don't need retrocausality, which is one of the quantum interpretations. It's simply not needed because these waves detect it and reflects back. So here's an analogy that I use simply as a way so we can see things. I take these disk magnets you see here and simply line them up. They kind of fit together into a column. And of course, you'll notice that this is the direction of movement. A neutrino then is an assembly of photons, which you see here. You'll also notice that the direction out of the paper has no surface area here, so neutrinos can travel at the speed of light. This then is an electron, which is another assembly, not only of photons, but of neutrinos. You'll note that this kind of a structure here looks like a neutrino. You'll note that this structure has 4 different magnetic poles coming out of each corner. It's these 4 different poles that are going to give the result of the Stern-Gerlach experiment instead of spin. It's this magnetic function, not spin. And of course, you'll note that if it travels in this direction, these are surface areas. And so the electron has surface areas in all 3 directions. So it is not going to travel at the speed of light, but is going to travel with a given orientation to minimize the surface area. And here's some papers that discuss this. Another interpretation of light is the Bohm interpretation. And its problem is, where does the pilot wave come from? The diffraction pattern minimum and maximum are at different locations for different photon energies. This is a spectrographic effect. And therefore, a photon must be the source of the plenum wave, which is the STO interpretation. Here's some videos which are quite important here because they're going to demonstrate this single photon stuff really has to be taken with a grain of salt. The STO, or I, in around 2012, developed a toy computer simulation model using the various assumptions of what a photon and ether is doing. So the first step for a particle model is to explain coherence in terms of particle action, which is what the computer simulation did. If you remember the structure of the photon, if you take each and every one of those HODs is producing a pattern, a wave pattern in the plenum, and then apply the equations that are well known for dipole antennas, and you get then this kind of an intensity pattern of waves directly ahead and off to the side. They have minima and maxima. Now, remember these little individual numbers here. So I start with photons in the simulation, positioned randomly and traveling in the same direction. Like the Bohm interpretation, each photon has a definite position and momentum. And you let it run for a while. And after a while, the locations of these photons, each of these little squares, as you see here, form lines. As you see here is the one that goes straight ahead, the E line, and each of these lines then corresponds to one of the directions you see there. Now, let's take a look at this a little closer, and you'll see what the importance of this is. Here's a slice of that, and you'll see here, 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 and here, there are voids forming. In other words, what's happening is the photons are forming into clumps, as you see. And these clumps are going to form something like the de Broglie wave, where you're going to have waves of particles hitting some structure. But that's going to then provide some impetus for the de Broglie. So this is what's happening with a single photon in our simulation. Here I positioned a photon between the screen over here and the mask, and the mask has a void in it. The waves that come from here are going to go to the screen and reflect back. The waves going to the rearward are going to go to the screen and reflect back, or they're going to go to the void area and continue on going. They won't reflect back. And so all the waves that come back to the photon are then going to direct it. And what it's going to do is direct it in terms of the well-known Fraunhofer type diffraction pattern, which is the same kind of pattern that you get with dipole antenna arrays. If a mask is simulated, a diffraction pattern ends up being on a screen. So we start with photons coming in, and here in the simulation, I'm tracking several photons. They come in, and some of them start to be directed towards the mass. Now, Newton noted this, and so did Young, that they tend to start moving towards the mass before it reaches the mass. The other thing we notice is that in this area and this area, there seems to be an assembly of photons. So these areas appear brighter. And this also has been noted by experimenters who look at diffraction images and masking. The other thing to note here is that photons that come in from the upper part are reflected towards the bottom, and those photons coming in below the center are reflected towards the top. This has been noted by several experiments I've done that it does actually appear to be the way it works. Now, you'll also notice that over on the screen, we're getting peaks, which then are the images we see on the screen. So the simulation is working. On the screen, when we count the number of photons that arrive at particular places on the screen, we'll notice that the intensity then fits very well for a Fraunhofer equation. And you can see the actual counts are these little lines, and the solid line here is the Fraunhofer equation. That if other matter is added, such as a detector, the plenum is changed. That is to say, the waves reflect off that detector and then change the direction of the photon. And this is as quantum mechanics suggests. The suggested simulation then is a very good fit for actual results. And there's the paper that talks about it.